When talking about the type of chemical bonds that we can have, it may be important to distinguish between the type of bond in which there can only be three, and the other kind is the type of material that you can see depending on the type of bond. So we have seen that the type of bond, when you're mixing a metal with a nonmetal, that bond can be ionic. When you're mixing a metal with another metal, that is metallic. And when you're mixing a nonmetal with a non-metal with a non-metal, you see a covalent bond. And what we have seen is that because ionic and metallic, these bonds are not directional, it means they do not care to whom they exchange the electrons. It means that you will end up just seeing lattices of solids. So for example, you will see the kind of material you will see an ionic solid. And what does that mean? Well, it will be a positive, negative, positive, negative, positive, negative. So when we talk about sodium chloride, for example, sodium chloride is not a molecule. It just tells you that in a lattice of not infinite but a large number of cations and anions, you have the same amount of sodiums and and chlorides. But that does not mean that there is only one sodium and one chloride going together. Actually, everyone is interacting with everyone. The same can be said with metallic, in which you will have what we call a metal solid. So you'll have, if you will, a lot of positive nuclei. They're all positive nuclei, and there's a pool of electrons all around, okay? But notice that these kind of bonds are non-directional. This atom interacts with this one, with this one, with this one, with many of them at the same time. This means that they do not form molecules. Do not form molecules. When you have a covalent bond, you have two situations. In one case, you could be seeing a molecular solid, or you could see a covalent network. So covalent network is a type of material that presents covalent bonds, but so does a molecular solid. What is the difference between them? Well, typically, the molecular solid is the most abundant one. Your material is made out of molecules. So for example, you have oxygen and hydrogen. There is a covalent bond in here and in here, but then there is, when you have another, and I'm drawing of course the structure of ice, these are covalent bonds, but these are not. These are intermolecular forces. Molecular forces. Okay, so when you are melting an ionic solid or a metal solid, they have high melting points, because when you're melting, you need to break the ionic or metallic bond. Therefore, and this takes some energy. When to break the structure of the solid, it takes a lot of energy because you need to break all these interactions. However, when you are melting a molecular solid, what you are breaking is not these covalent bonds, you are breaking the intermolecular forces. Okay, so I have a simulation to express that, so let's see if that helps a little bit. Let's see, for example, imagine that this is just a small part of an ionic solid. What happens if we try to melt it? Well, we're going to increase a lot of heat. Let's see, and notice that all the interactions are breaking until, so you see, so you have to actually separate the positive from the negative. You have to break the ionic bond. Okay, so that's for ionic bonds. This is why when we look at here, we said that they have high melting points because when melting the solid, it takes a lot of energy. You need to break the ionic bond. How does that change for a molecular solid? In this case, it will be, oh, sorry, let's play fair. Notice that this is a liquid, um, so we don't have a solid, but it's a liquid. What is this liquid made out of? Well, this liquid is made out of already molecules, okay? So when you melt it, or in this case you boil it because you already melted, when you boil it, notice that what evaporates is not the different atoms. That means that to evaporate, we just get rid of the intermolecular forces, not the covalent bonds among them. So this, the bond between hydrogen and oxygen is a covalent bond that doesn't need to be broken to melt or boil the compound. We just needed to break the intermolecular forces, whatever attaches this molecule from the other one. So there you go. Your molecular solids will typically have a low melting point because you just need to break intermolecular forces. Intermolecular forces. Okay. There is one exception of when you see covalent bonds, and this when you have a covalent network. And that covalent network is present only when you have carbon, either diamond or graphite, or you have silicon, silicon oxide. In this case, what you have still have covalent bond, but you do not have molecules because carbon and silicon can form up to 4 bonds. This means that your carbon is not in a form of a molecule. It's spread all over the space. So to melt carbon diamond in this case, you actually because there's no molecule, you need to break covalent bonds. So covalent networks will have again a higher melting point. Okay, so hopefully you see the trend. Typically, because the covalent bond is directional, you will typically see molecules. The type of material will be a molecular solid, with the exception of carbon and silicon because it can form 4 bonds, that is in all the directions of the space, so you don't see molecules, and therefore because there are no molecules, when melting that compound you need to break something as strong as the covalent bond, and that takes a lot of energy. So high temperatures, high melting point.